Lesson 84, we're going to be talking about the degree of equations, and we're also going to be talk about what can happen when we have systems of linear equations, so two lines. What happens when we try to solve those? What are the different possibilities? So first, vocabulary that you need to copy down and know. Degree means if you have more than one variable, you take all of the exponents on the variables and add those up. If you only have one variable, it's the exponent on the variable. And I'll even show you what happens if you don't see any variables right away. Like on this one. No variables means the degree is 0. You could think about that as, oh, 2 is really 2 times 1, and anything to the 0 is 1, so that's also equivalent to 2x to the 0, so that it is still the exponent on the variable. But usually easier to just say, oh, no variable, degree is 0. So, you guys, what's the degree here? It's going to be 3, because that was x cubed. Now, this is one where we have a bunch of variables. The 2 is easy to see, but we've got to include these invisible ones. So we need to do the 2 plus 1 plus 1 plus 1, giving us 5 for that degree. And you guys here in class, shut up. What's the degree here? 1, because there's just that invisible 1. So that much is pretty easy. I like it when we get easy material going on here. Okay, if we have a polynomial, so that means we could have more than one term, something plus something minus something. We look at all of the terms, and we're going to take the biggest degree for any of those terms. So if I have one like this one has degree 2, this one has degree 1, this one has degree 0, the biggest one is 2. We also, if it has one variable and is degree 2, we call it a quadratic. Like the quadratic equations we've been solving if that equals 0. Okay, this one, what's the biggest degree for you guys here in class? Shout it out. 3 is going to be our biggest degree, and if we have one variable and it is degree 3, we call it a cubic equation. Okay, now this one, what's the degree for the xy? It's going to be 2 because there's an x to the 1 and x to the 1, and the degree of 5 is 0 because there's no variable. So this is degree 2, but we don't call that a quadratic because we have 2 different variables in it. And then this one, we've got the 1 on the left, and we've got the 1 on the right, so it is degree 1. And that's a linear equation when we have the degree 1 in there, but we've got the y equals the x. So that's mostly review, just checking a little bit of vocabulary. Okay, another thing that is more or less review for us, because we've been doing a bunch of these by hand, graphing them by hand, graphing them on the calculator, doing the algebra by hand. If we have linear equations, that means we are graphing lines. And what we have been doing up to this point in time is we've been graphing something like maybe this, and maybe this, and then what have we done when we got to that point? We found the intersection point, which is the solution. So in this case, it happened to be 2, 1. But most of the ones that we've been doing, we have had one solution to that system. Now, if I have 2 linear equations, What else could my lines look like? Somebody at home, unmute and answer for me. Do two equations for lines always mean two lines that cross at one point? Clayton, you're shaking your head no. What else might happen? Clayton, unmute. What else might happen?
I don't know.
Oh, I thought you were shaking your head no. Okay, if I have two equations for lines, do those lines always cross at a point?
No.
What else could happen?
They could be parallel.
Okay, so another thing that might happen is we might have some parallel lines. And if that were the case, I might have some that look something like, let's see, what do I want to do here? I might have one like that, and then I might have one that looks like that. And in that case, I would have no solutions. Now there's one other thing that could happen. I give you two equations, the linear equations. Anybody remember what else might happen? James? Those still cross at one point. It's a special case of the crossing at one point. So let me get a couple of lines up here. So I might have, I'll do something with a negative slope here just because. I might have one like that. And then I might have another equation. And if I graph it, it might look like that. So I could also have two that are really the very same line. In that case, we have infinitely many solutions, and I'll write that up there in a moment, because every single point on there would be a solution. Every single point on the first black line is also a point that is on the second blue line, the way that I graphed them. Now, this point off here is not a solution. Only the points that are on those lines. Okay, now let's notice a few things about these. I'm going to give you some other vocabulary that you're going to make sure you write down and really learn. When I have one solution, I have different slopes and they might have the same or different intercepts. The slopes do not have to be one positive and one negative. I could have a steep negative one and a not so steep negative one. I could have them where they cross right on the y-intercept. That's when they might have the same y-intercept. What's true about parallel lines? Do they have the same or different slopes? Connor, do they have the same or different slopes if they're parallel?
They have the same slope.
And Cannon, what about their y-intercepts? If they're parallel, can they have the same y-intercept or do they have to be different y-intercepts?
They're different.
So if they are parallel, they have to have the same slope and different y-intercepts. If they are the same line, well, if they're the very same, they've got to have the same slope and the same intercept, right? Okay, a little bit of new vocabulary for us. If it can can be solved if we have one solution or more than one solution. It is consistent. If we have no solutions, then it is inconsistent. So if we use this new vocabulary, do we have a solution on the first type? Because we had one solution, so it is consistent. We said no solutions on the second one, so inconsistent. And write a couple other things up here on this one. We said that this one has infinitely many solutions. Which were all the points on the line. Since the two lines were the very same thing, everything on one was also on the other. Since it has solutions, this one is consistent. The other new vocabulary word is independent or dependent. If they are two different lines, they're independent. If they're the same as each other, they really depend on each other. They can't get separate from each other at all. So this one is dependent. But these other two, we had two different lines, so they were both independent. You need to know everything that I just wrote up on the board. You need to be able to classify consistent, inconsistent, dependent, independent. You need to be able to say one solution, no solution, infinitely many solutions. You need to be able to say they're parallel or they're the same line. You need to be able to use what I wrote up there about if they have different slopes, then they will intersect somewhere. If they have the same slope but different intercepts, they're parallel. If they have the same slope but the same intercept, then they're really the same line. So does everybody have that vocabulary copied down? Anybody need me to scroll down to get some of what I had down there a little bit lower? Now, we don't always want to go through all of the steps of graphing it to know what's going on. Maybe not even all the steps of solving it. Maybe we only want to know, do they intersect at one point? Are they parallel? Are they really the same line? So let's review. You've seen this before in Algebra 1. What happens if you use substitution or elimination to solve and you don't just get a point? You know if you use substitution or elimination and you get x equals this number, y equals that number, that they cross at one point. But these second two cases, what kinds of things happen? So if I took this first system, and let me do this one maybe by elimination, looks pretty easy. If I multiply this second equation by -2, I get minus 2x minus 4y equals minus 12. Check my work, is that correct? I didn't drop any minus signs or anything, right? And then if I just recopy this one, 2x plus 4y equals positive 12, what do I get, Riley?
Both x and y cancel.
Yeah. So what does that leave me on the left? Leave 0, and on the right?
0.
So I get something like 0 equals 0. James, when does 0 equal 0? Always. If you get something that is always true, 0 equals 0, x equals x, 5 equals 5, always true. Doesn't really matter what I pick for x. It's always true. That means same line. Always true. Infinitely many solutions. There's that one here in a moment. Just finish writing some things down about it. So infinitely many solutions. If they're really the same line, These directions asked us to classify. Oh, no, it didn't. Next one will. So if they really were the same line, we do have solutions, so it is consistent. The same line, they can't get away from each other, can't break away and be an independent, like you guys are, I'm sure, overly eager to break away from your parents and be independent. These two lines can't ever break away from each other and be independent, so they are dependent. Now let's try the other one. This time let's do substitution, just so we've done it once each way. If you did substitution, you still would have gotten something that's always true. 0 equals 0, 5 equals 5, whether it was elimination or substitution. This one I'm going to let x be 6 minus 2y and put that in for that x in the first equation so that I can have 2 times 6 minus 2y plus 4y equals 11. 12 minus 4y plus 4y. And my y's cancel. 12 equals 11? Never. That's impossible. If it's impossible, that means I have no solutions. If you had done it with elimination, you would have also gotten something that is never true. If we have no solutions, we know that means that they are really parallel. And if they have no solutions, they can't be solved, they are inconsistent. And if they are two different lines, they have broken away from each other and gotten their freedom, so they are independent. Reading the directions there. And we have to draw a sketch, which I'll talk about, what we have to be a little bit careful of when we do that. So, what do you think we ought to do as we look at those? I'm waiting for an idea. You can either unmute at home, or you can shout something out here in class. What do you think we ought to do? How would we start solving? Riley, what are you thinking?
Elimination.
I kind of like elimination too. I really don't want to get y equals by itself and get some weird fractions or anything like that. So which variable do you want to get rid of?
X.
Okay, so if we get rid of the x, maybe multiply the top one by a -3, giving us negative 6x minus 9y equals 18. So 0 over here on the right. And let's see, then what do I have on the left? 9y, which means y is 0. Oh, if I get a number that's true, then I could plug back down and get x if I wanted to. This did not say I had to actually solve it. So if I get numbers, that means I have 2 lines that cross. One solution. So that's one of the things we were supposed to say. Consistent or inconsistent? Everybody at home type and hit enter real fast. If I can get a solution, is it, which I'm doing, I know what the y is and I could plug in and get the x. So consistent or inconsistent and hit enter. So good job they're saying consistent because we can get an answer. And we had 2 different lines. They have their independence from each other. Now for a sketch. We are not going to just do any old sloppy sketch that they cross at one point. We're going to try to be a little bit better students than that. I at least want the appropriate slopes. So I do need to do just a little bit of work here. So I would say on this one, I've got 3y is minus 2x minus 6. So I'm going to divide by 3, and I'm going to have a negative slope and a negative intercept. So let's see, a negative slope and a negative intercept. So maybe something kind of like that. And then for the other one, same thing. I could have said 18y is negative 6x minus 18. And if I divide by 18, I get an intercept of negative 1 instead of negative 2. And the slope's negative 1/3, so not quite as steep. And so I'm going to draw a second line that looks something like that. Now, I happen to know that when they cross each other, y was 0. That was why I made it cross at that intercept. So everybody good with that? Give me a thumbs up if that's making sense. Are you guys both good? Okay, then another one. Let's see what's going on with this one. Let's take a look at those. And what are some things we're noticing there on those two? James, you notice anything?
Well, we could use substitution.
We could do substitution on that. I also noticed the first one isn't really in my normal order. What if I rewrote the first one? 3y equals minus 6x plus 12. Now, does anybody notice anything about the way that I've written them now? Take a look at those two. Everybody at home, are you looking at these two equations? Clayton, I need you on screen. Abby, you notice anything about those two, the way I've written them now?
They end up with the even numbers.
What do you mean by that?
Like when you put the y's, x's, and the other numbers together, it'll be 4y equals negative 8x plus 16.
I could multiply the second one by 4. I'm not sure that's going to help me a lot. James, did you notice something else?
The bottom one, if you multiply it by 3, it equals the top.
Okay, so if we didn't want to have to waste our time doing substitution and elimination, if we took this bottom one times 3, we would have 3y equals minus 6x. Which means infinitely many solutions, has solutions, so consistent, but dependent. They have not been able to break free from each other and go live their own lives. They're stuck there together. Then for a sketch, this one already tells me positive 4 for the intercept, negative 2 for the slope. And that's all I'd have to do there. Questions from anybody on that stuff?